When it comes to calculus, some of the first things that come to mind are derivatives and their partner, integrals. For this video, we're going to be focusing on integrals, more specifically, a version called triple integrals. While most calculus students have a general understanding of how standard integrals work, it's not uncommon for them to look on in fear as integrals begin to stack up. As soon as you learn how partial derivation and integration works, though, it clears up pretty quickly. An interesting problem arises, though, in certain circumstances with triple integration. Some shapes are not as conducive to integration in the Cartesian coordinate system, so mathematicians thought, well, why don't we make this easier? This is what they figured out. So, to begin this system, let's refresh on how location is described in the Cartesian system. A point is represented by its x, y, and z Cartesian distances from the origin point. For many common shapes in 3 dimensions, this description of space works just fine, but for some shapes, it gets more complicated. For instance, cylinders. A new system of describing location was created to help describe shapes like this, aptly called cylindrical coordinates. It starts exactly like polar coordinates, with a radius r and an angle theta, but then a vertical distance z is added to account for all locations in 3D space. Still, what if we wanted to describe shapes relative to spheres? Thus, another coordinate system, spherical coordinates, was born. Again, the coordinate system starts with polar coordinates, but the radius here is called rho. The biggest difference between cylindrical and spherical coordinates is the way the third dimension is addressed. Instead of doing a linear distance up, another angle, phi, is used to describe the angle from the vertical. If you've done cartography or looked at a globe before, you've seen spherical coordinates, as the measures of latitude and longitude are the spherical measures of phi and theta, with the prime meridian being at theta equals 0 and the north pole at phi equals 0. Now that we know the other coordinate systems, how do we integrate in them? Converting between these coordinate systems is key to being able to change the bounds of integration and the function being integrated over. This video is not about these conversions though, but I'll put the conversions between Cartesian and the other 2 systems here for your benefit if you want to pause the video. Now that we understand the new coordinate systems, how do we triple integrate in them? As you probably remember, triple integration of any coordinate system follows this form. The triple integral over volume V of f dv. F is a function that is to be integrated over and is defined in the coordinate system of integration. In essence, as long as you can convert it from a form with one system's variables to the system you are integrating in, it really doesn't change anything. The bounds of integration are similar. You draw the volume of integration and redefine the volume in terms of the new coordinate system. The definition of dv is more interesting though. In a triple integral, similar to a regular integral, dv is by definition the infinitesimally small chunk of volume over which the function f is being summed up. In Cartesian coordinates, we can think of dv as a rectangular prism, with side lengths being the delta or change in x, y, and z. These deltas get smaller and smaller as dv goes to 0, so they can be rewritten as dx, dy, and dz. This means that dv equals dx, dy, dz. This easy visualization appears to break down, though, when we move into cylindrical and spherical coordinates. The dv chunk for a cylinder is a wedge of sorts, which appears like a piece of a square donut. This clearly isn't a rectangular prism. Or is it? See, dv is not the volume of this wedge. It's the volume of the wedge as the wedge gets infinitely small. And while it may be hard to see, as the wedge gets smaller and smaller, it approaches the shape of, you guessed it, a perfect rectangular prism. Thus, we can treat it like a rectangular prism and just multiply the dimensions to get its volume. So, this side is delta r, or like before, we can write dr because it's really an infinitesimal. This side is dz, but what about this one? It could be really tempting to simply write d theta, but that's not a length, that's an angle. To get the length of the side is the same as getting the arc length of a portion of a circle. To get the arc length of a part of a circle, you just multiply the radius times the change in angle. So this side is actually r d theta. Multiplying this out, we get that dv equals r dr d theta dz. Let's look at spherical coordinates now. Again, the dv for a sphere is nowhere near a cube when it's this large, but just like a cylinder, as the chunk gets smaller and smaller, it again approaches a rectangular prism. So, just like in Cartesian and cylindrical, what are the side lengths? This one is d rho, but the other two are a bit weirder. Let's start with this vertical side. If we look closely, we realize that no matter what theta is, this arc remains the same. Because no matter what theta is, it's just which direction you're pointing. It doesn't change the length of the arc. Again, it is an arc of a circle, so the arc length formula dictates that the length of the side is going to be rho, in this case our radius, d phi, the vertical angle. All we have left is the d theta term, so let's figure that one out. It's also an arc, so we're going to need to multiply that d theta by the radius rho, but there's one more thing. As phi gets smaller, that arc length gets smaller because the chunk gets compressed as it goes towards the top of the circle. As it turns out, we need to multiply our rho d theta by sine phi to get the arc length, and as a result, the side length. When we multiply this out, we get dv equals rho squared sine phi d rho d theta d phi. Now that we know dv for cylindrical and spherical coordinates, we can solve triple integrals in both systems. Let's try some examples of triple integration in cylindrical and spherical coordinates. Let's start with an integral in cylindrical coordinates. Let's start with the standard form for a triple integral, but let's change out f for the f with the correct variables. Let's also substitute in the proper dv for cylindrical coordinates, which is, if you remember, r dr d theta dz. Now, we're going to be trying to find the volume of a cylinder and to verify that this dv is correct. To do this, we're going to want to set the function inside the triple integral to 1. The reason for this is that the function can effectively be thought of as a density function for the volume being integrated over. If we set this function to 1, the triple integral now gives us the volume of the region being integrated over. Now, let's set the bounds of integration. For r, the radius goes from 0 to r, our big radius. The angle of theta goes from 0 to 2 pi to create a complete circle. And our z goes from 0 to h, the height of our cylinder. Now, we can ignore the 1 because it multiplies through. Then let's integrate r. The integral of r is r squared over 2. If we evaluate this at r equals big R and r equals 0, we get r squared over 2 minus 0, which can be simplified to r squared over 2. Now we integrate theta. The integral of d theta is theta. If we evaluate theta at theta equals 2 pi and theta equals 0, we get 2 pi minus 0, which simplifies to 2 pi. So we now have r squared over 2 times 2 pi, which can be simplified to r squared pi. Now let's integrate z. The integral of dz is z. If we evaluate z at z equals h and z equals 0, we get h minus 0, which is h. Then we can rearrange all of the values to get the cylindrical volume formula. Volume equals pi r squared h. Now, let's do another example, this time in spherical coordinates. Again, let's start with the standard form for a triple integral. And let's substitute in the function written in spherical coordinates. Let's also substitute in the proper dv for spherical coordinates, which, if you remember before, is rho squared sine phi d rho d theta d phi. We're going to be solving for the volume of a sphere, like we did the volume of a cylinder, so we're going to replace the function with the value 1. Then we're going to need to set the bounds. The bounds for rho, which is the radius, is going to be from 0 to r. The bounds for theta, which is the angle around, is going to be from 0 to 2 pi. And the bounds for phi, which is the angle from the vertical, is going to be from 0 to pi. Again, we can multiply through the 1. Then we can start integrating. Let's start with rho. The integral of rho squared is rho cubed over 3. If we evaluate this function at rho equals r and rho equals 0, we get r cubed over 3 minus 0, which becomes r cubed over 3. Now let's integrate theta. The integral of d theta is theta. If we evaluate theta at theta equals 2 pi and theta equals 0, we get 2 pi minus 0, which becomes 2 pi. Now let's integrate phi. The integral of sine phi is negative cosine phi. If we evaluate negative cosine phi at phi equals pi and phi equals 0, we get 1 plus 1, which is 2. Then we multiply the numbers through and rearrange the variables, and we get the volume of a sphere, 4/3 pi r cubed. Just to recap, triple integrals in each of these coordinate systems follow this pattern, and the bounds of integration are found by visual analysis. When we look to find dv for our systems, we see how the infinitesimally small chunk approaches the shape of a rectangular prism. To find its equivalent value, we find what each side is and multiply them together. Through this, we find that dv equals dx dy dz in Cartesian coordinates, rdr d theta dz in cylindrical coordinates, and rho squared sine phi d rho d theta d phi in spherical coordinates. And to think, all this math because someone just didn't want to do it the hard way.